Do you have your note sheet in front of you, my friends?
Yes. Right
Oh,
here.
okay. So you've done a little bit of integral calculus in that you've done anti-differentiating e to the x or x squared or whatever. It doesn't really mean much to you right now. Right now it's just something you do, you integrate, and who knows what it means. And today will be pretty much another lesson like, here I do some stuff and I don't really know what it means. Please, I beg you though, when we go to find area under a curve, and you first and foremost come back to me and say, area under a curve, who gives a rip? It matters. It matters. It's a huge, huge idea of calculus. There are so many reasons you would want to find area under a curve. And I guarantee you, I will get you lots of applications. So many that you're sick of the applications to this. But today we're just going to talk about the how you do it, not the why. Right? So trust me, there is a point of it all. As we do a lot of this kind of symbol pushing, it's not just some obscure math exercise that only math nerds like. It's good stuff. All right, you with me?
Yep.
Okay, cool. Now, for the topic of the day, you're going to be taking a curve and finding or estimating area under it. So let me introduce the idea this way. Would you draw me a square root curve that's fairly nicely drawn to 8? Right? In the interest of scale, would you then half that, call it 4, quarter it, calling it 2 and 6, and let's go all the way down to showing the 1, at least you don't have to label it with me. All right, now, our goal is to estimate the area under the curve. Now, if you think an area under the curve, doesn't the area go forever? Well, it's kind of implied always that you're talking about the area under the curve, but down to the axis and stopping at the axis. So when I say area under the curve, it's really this region. Don't be a wise guy and say, oh, it goes forever. Okay, yeah, just get over it. All right, you with me? So we're looking for that yellow area. You with me?
Yep.
Okay, cool. Now, it's a kind of a curvy region, so I don't have some kind of geometry formula for this. It's not a circle, it's not a half circle, it's not a quarter circle, and I guess a triangle would do a decent job, but we use rectangles. Why we use rectangles? Well, you'll see. It goes to the fundamental theorem of calculus later on, but for now, we're going to use rectangles. Now, I can estimate the area under the curve here using at least 5 different rectangle methods. I could use left-hand rectangles, right-hand rectangles, midpoint rectangles, lower rectangles, upper rectangles. And we'll get through all of these in class today, but just know that there are a couple different ways to go. The first, though, is how many rectangles. I could use, don't need to write this down, but I could use this in green. I could use 1 rectangle to estimate the area, and it would be a gross overestimate, and it would be simple, but it would be way too much area. You with me? Mm-hmm. All right. I could use, say, I'm going to do 1 rectangle from 0 to 4, and 1 rectangle from 4 to 8, and that wouldn't be bad because that would be less error, the error being this overestimating region, right? So one of the big ideas of the day is 2 rectangles is better than 1 rectangle because there's less error. Likewise, as you might expect, I could say instead of 2 rectangles, I could go 4 rectangles. And then the error is even less. In fact, I could take the number of rectangles to infinity with a limit, and I could get the perfect area. And there would be this beautiful blend of there are infinitely many rectangles, but as you add the rectangles, what happens to the base of each rectangle? Smaller and smaller. So you actually get infinitely many microscopically thin rectangles that get you the perfect area. What do you reckon that microscopically thin change in x is?
Delta x.
dx. Yes, yes, yes.
No.
Would that give you a perfect area, or would it still be like
It-
a tiny?
It would approach the perfect area. Good, that's a good call, yeah, it would approach the perfect area. But we could get the perfect area with calculus, and we will talk about that. That, at its heart, is the fundamental theorem of calculus. Infinitely many, infinitely thin. And that right there blows my mind, because the area of each rectangle goes to, you just told me the base of each rectangle goes to 0. Therefore, the area of each rectangle goes to 0. And yet the number of rectangles goes to
Infinity.
And so there's this play in between of infinitely many, infinitely small rectangles, and it approaches perfection. It's the fundamental theorem of calculus will blow your mind. For now, we're going to do just a finite number of rectangles, and in this case, I'm saying 4. All right.
That's boring.
Now, yeah, sorry. So when you do 4 rectangles, you use these to find the base of each rectangle. The base of each rectangle, which we're going to call delta x, is the total region divided by the number of rectangles. So in this case, because I have a region that's 8 wide, and I'm dividing it evenly into 4 chunks, each base will be 2. Each base is 2 in this case, not in every case, in this case. You with me? All right. That's what I mean by subdivide the x region into 4 equal parts. These give you the bases of the rectangles. The base, which is delta x, I will typically call this b minus a over n. B and a represent the endpoints of the region, and n represents how many rectangles you're using. But for now, I think the words are better up here. Total region divided by the number of rectangles. All right? You with me so far?
Yeah.
All right. Now, in terms of getting the heights of the rectangles, the first rectangle I'm going to do in green, and it's goes from an x of 0 to an x of 2. Now the question is, all right, where's the height? Well, the height is tied to the curve. This is what matters. This defines the height, or defines where the height is. Okay? If it says right-hand rectangles, then in the subinterval from 0 to 2, I go to the right-hand side, then I go up to the curve, and I say that is going to be the height of the rectangle from 0 to 2. Now to complete the rectangle then, from 0 to 2, it's got to be like that. Now certainly that's going to be an overestimate, because that's got some area there in the rectangle that's not truly in the yellow area. You with me? All right. So in the second subinterval, from which is from 2 to 4, I use the right-hand side. I find that side, go up to the curve, and that's going to be my rectangle height from 2 to 4. So as far as where I draw the rectangle, I draw it over, and that's my second rectangle. All right. In rectangle 3, I use the height at 6. So I go to 6, go up to the curve, draw over to the left, and there's rectangle 3. And for rectangle 4, I go to 8, draw over, and there's rectangle 4. Now, these 4 rectangles will overestimate the true area under the curve. Do we all agree? Okay. And that's okay. Now, because it is an estimate, we need to say A, which this represents the true area, is approximated by approximately these 4 rectangles. Base 1, height 1, plus base 2, height 2, plus base 3, height 3, plus base 4, height 4. Right? All right. Now, I do that in my notes, and I'll probably do that for a day or two, but eventually you'll start going to a little different form, and we'll skip a few steps. Now, In this case, because all the bases are the same, you can factor out a generic base. All the bases the same here. And the reason is because they're equal subdivisions. You will eventually sometimes do some that are unequal subdivisions, but these are equal subdivisions, equal bases, right? The heights are still in. All right. Now, this is where we go away from the more geometry and say, well, let's go more to x, y, f of x. The base is delta x. And the height, doesn't the height really come from the function? Now, I can't just say f of x each time. I need to show somehow they're different. So you're going to say the function at a first x. And then the next height will be a function at a second x. And then a function at a third x. And then the function at the fourth x. For 4 different heights. Are you with me? All right. Will you parenthetically say later we will use sigma, which is a Greek S, not E, it's an S for sum, and it stands for the sum of many things in a pattern, and it's delta x, f at different x's that count up, and in this case it would count up from x starting, or I starting at 1 and ending at 4. But if we wanted perfect area, instead of going to 4 rectangles, we'd go to. All right. We will use summation notation a lot. I know it's intimidating on one level, but it saves so much writing. We're going to have to use it, all right? Not to mention it's huge in Calc 2 that you get fluent with us. So we will go to that later, but for now we're going to use expanded form. All right, so going to this problem, I hope you still have enough room. What is delta x for this problem? 2. Yeah. Delta x is 2. It's tempting to go straight to the square root function, but instead I want you to communicate at what value you're finding the height. So don't jump to square root of anything yet. Instead, tell me, for my first height, I'm going to use f at 2. Height 2 is f at 4. The third height was f at 6, and the last was f at 8. All right. At that point, then you can use your calculator to calculate this. If you want to do this step I would consider optional. Root 2 plus root 4 plus root 6 plus root 8. If you wanted to write that, great. But it doesn't have to be said. This must be said. That's required. You've got to communicate, hey, this is the points at which I found my height. And you slap that in the old calculator. Slap. What is it? It should be bigger. You forgot the 2. You did? I would have expected bigger.
17.384.
That's better. 17.384. Are you with me? Let me give you, it's always good, at least for a thinking person. Sometimes people just fly blind and say, I guess that's right. But in terms of thinking, wouldn't you agree that the enclosing area is definitely 8 wide? And as far as the height, I don't know what the square root of 8 is, but I know that the square root of 8 is definitely less than 3. So that area's got to be less than 24. Got to be, right? And so this coming in at 17, see, that's easy. You with me? Okay. All right. Let's go to left hand. Would you redraw? Leaving yourself some room for the calculus. And mark 2, 4, 6, and 8. Okay? Because it's 4, because of the 0 and 8 and 4, delta x is still 2. We're going increments of 2. You follow? Okay? As far as drawing the heights now, it says for left hand. So in each subinterval, go to the left end point to draw the height. All right, so from 0 to 2, I go to the left edge, which is 0, and draw the height. Now that kooks students out because it isn't what. Yeah, I understand. The height is 0. It is what it is. Get over it. All right. From 2 to 4, I go to the left edge, and the left edge is 2. I go up to the curve, and when I draw the triangle, do I go back this way into the 0 to 2 range, or this way to the 2 to 4 range?
Right.
So doesn't that mean the rectangle is now going to be below the curve? And therefore my area will now be less, or underestimating the true value, okay? Which actually is great, because if you could fence in a true value with an under and an overestimate, all the better. Now you've got a region for it. All right, let's go to 4 to 6. I use the height at 4, and I draw over towards 6. And then finally, I go from 6 to 8, drawing at 6, and I go over to 8. So every area should be a little under. You agree?
Yep. Yeah.
All right. Now I'm going to this time skip all the base height kind of work and start here. The area is the factored out base, which is, oh, that should be an approximation, yes, thank you. The factored out base, which is delta x, and f at x1 through, you may use a little dot 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 action through f of x4. You follow me? Okay. What is delta x in this case? 2. Now here's where it starts to get different, because I'm using left hand. The first height is f at 0. The second height is f at 2. Height 3 is f at 4. And the last height is f at 6. If I slap that into my calculator, or 2 times root 0 plus root 2 plus root 4 plus root 6, I should get something much less than 17 for sure. 11.727. All right. So the true area is probably between, not probably, is between 11 and 17. You follow? All right. I told you there are at least 5 different rectangle estimation methods. Let's go to number 3, midpoint rectangles. Midpoint rectangles, again, draw the curve. 0 to 8, half and quarter. Okay? Now, midpoint, the name, so it's still, do you agree it's still 0 to 8 with 4 rectangles, delta x is still 2, we're still going by 2s. You're not always going to go by 2s, that's just, we're trying to be consistent so you can just focus on the heights right now. The delta x will change. All right, so what do you reckon midpoint means in terms of where I draw my height? I draw my height at the midpoint y or the midpoint x? The midpoint x of each sub-region. So in the first case, I'm not going to use the left of 0 or the right of 2. I'm going to use the middle of 1. All right, now, so what will that look like? Well, you go up to the curve. When you go to draw the rectangle's top side, do you draw it left, right, or both?
Both.
Yeah, you draw, at that height, you draw across from 0 to 2. Right, and the next subinterval, is from 2 to 4, you draw your height at 3. That doesn't show very well. Okay, so you go up to 3 and you draw across, so you have a top edge going from 2 to 4. Cool. And then, let's bring, whatever, just decide. From 4 to 6, the middle is 5. That's really long. Okay, and the last is 7. Is 7. Okay, cool. Now, in terms of the area, it's approximately delta x and f at different heights through 4. You follow? What's delta x in this case? 2. As much as I'd like to just start saying square root of this and square root of that, you need to say f at this and f at that. So, your first height is f at 1, then f at 3, then f at, and then f at 7. Then throw it in your calculator. If you want to write the next step of 2, root this and that, that's fine, but it's not required. The previous step was the one that was required. And what do you get? 15.28. 228. Does that make sense that was between the other two? Yeah, which one do you think is the best? Why is midpoint the best in terms of the error or the area of the error? Yeah, it's got over and underestimate. Now, those don't perfectly cancel out, and that has to do with the concavity of the curve. But midpoint is the best. Okay, cool. Yes, hit me.
So, are like the right and the left hand ones like equal distance away from the midpoint or something like that? Or maybe like
Good question. No, that has to do with the nature of the curve. There will not always be halfway in between. Yeah. Okay, good question. I didn't think about that. It'll be in the middle, but not always perfectly. Okay, now consider this. We need to also be able to. Apparently, I don't have those two bottom problems. I think this will be better illustrated. I think I skipped those for a reason. Those are better illustrated from a table perspective. So skip those last two, and I'll come back to them if I feel they're necessary. But I think this is. I rethought my notes, and I think this will go better, right? Now we work from equations, or analytically. You should also be able to work numerically, or from a table of values. Here I give you a function. And in this case, I don't really tell you what the graph looks like or the equation is. I just give you a bunch of points. A picture is helpful but not required. And the more of these you do, the less and less you'll rely on the picture. But starting out, I think I'm going to do a really rough picture. And I'm actually just gonna communicate to you how quickly this can go. So here's the deal. I'm gonna need to go to 18, 3, 6, 9, 12, 15, 18. The y values look like they're up to 8. 8, 0, 5, 3, 7, 6, 4, 9, 3, 8, 15, 0, 18, 3. Okay. Now that took me roughly 30 seconds to do. That was not a huge time commitment. It was, and to me, I'm a visual person. You kind of, at your age, you probably start to know yourself a little bit. You know, if you're visual or auditory or tactile, you need to touch something to learn from it, whatever. I'm a visual guy. So it helps me to have a picture. If it doesn't help you, then you can bypass the picture. Now, in this case, we're trying to estimate the area under this curve, whatever it might look like. Dots alone doesn't tell me the whole picture, but it gives me an idea. Using 6 right-hand rectangles of equal subdivisions. So let's start by finding what's delta x. Delta x is 3. How'd you get it? 18 minus 0 divided by 6, so it is 3. We're starting at 0 right now, but not every region starts at 0. So sometimes it'll go from 2 to 5 or 2 to 18 and so on. So you always need to start the end and the number of subdivisions to find the delta x. Are we cool with delta x? All right, now we set up our area. The area is approximated by delta x times the heights of a bunch of rectangles. This time it'll be x1 through x. What? It'll be 6 because we started at 1, it'll end at 6. I see what you're saying, 7. We'll actually get to something like that later, but right now it's just 6 rectangles. You with me? There should be 6 heights for 6 rectangles. We cool? All right. Throw in your delta x, it's 3. Now here's where right hand, left hand matters. If we're using right hand rectangles, then in our first subinterval from 0 to 3, we use 3. So the first height will be f at 3. Would you write yourself a note, please? Show this. Do not go straight to the table values. You shouldn't make the reader have to go back and say, oh, he put in a 7 there. Where's that from? It should be clear. I used f at 3. All right? I shouldn't even need to see the table to know what you're doing. All right. What about the next then? F at 6, then F at, and F at. All right. Then feel free to go to the table. Basically, I'm just starting at F at 3, which is 7, and reading off. So I'm going to go 7, 4, 3, 8, 0, 3. You see where I'm coming from? You do not have to show that stuff. If you then add here, what do you got? 11, 14, 22, 25. 25 times 3. 75. All right, there's my estimate, and we're good to go. You follow? Now, without seeing the actual graph, I can't tell if that's an overestimate or underestimate. That's not as clear here, so that part would be lost. The area using 2 left-hand rectangles. Let's see how you're doing. Would you give this a go, please? ¿Listos? Okay, what's delta x here? 9, all right. In terms of the height, I only have 2 subdivisions and I'm using left hand. So the first interval is from 0 to 9, and for the height I use f at 0 because it's the left side of the subinterval. The next subinterval is from 9 to 18 in green. I use the left hand side, so for the second height I use f at 9. Right, that means my estimate should be something like 9 times 5 plus 3. And so you should have 72 as an estimate, yeah? Okay, cool. Let's go to midpoint. Would you give midpoint a go? And then we'll compare. do we have for an estimate? 60, cool. Delta X is? 6. Height 1 is F at? 3. Height 2 is F at? And height 3 is F at? 15. Okay, and after substituting and multiplying, we get, we said 60, yeah? Okay, let's go on to another idea. I said there are 5 different rectangle ideas. Okay, so the next, besides left, right, and midpoint, actually, let's go with some abbreviations. I don't do this a lot, but some books do. When you say right-hand rectangles, would you write under here R, RAM? That's right rectangle approximation method. So if you go to college and they use the abbreviation, hey, use RRAM to estimate to get an area. That's the right-hand rectangle estimation method. The other one obviously is LRAM. And the midpoint is M. Okay, midpoint rectangle approximation method. Now we're going to use none of those three. Now we're going to use lower and upper. Sometimes there is a case, especially in real life applications, you've got to make sure that you have either you're covered your tush. So either you've got a definite lower estimate or overestimate, depending on the case. That's what these cases are for. Estimate the area under F using 6 inscribed, which is another word for lower. Lower is actually more common, rectangles of equal subdivisions. And if it's in the case of lower, then write yourself a note. In each subdivision, use the lowest Y value for your height. Right? So if I am using 6 inscribed rectangles, then what's delta X? 3. Okay, so I'm going to go 0 to 3, 3 to 6, and so on. All right, so my area approximation, delta X will be outside, and I'm going to multiply by 6 different function values. Do you see where I'm coming from? Yeah. Okay, the delta X we just said is 3. We're all good. All right, now this is the step that's most important now, because it's not going to be some obvious pattern, F at 3, F at 6, F at 9, F at 12. It could look like it's all over the place in the middle, and that's why it's important to communicate. So in the first subinterval, I look at the 2 Y values, and I choose the lower value. Here's the lower value, and now fight the temptation to say, oh, it's 5, and write 5 there. You've got to communicate, this is where 5 came from. And you have to say F at 0. Okay? The next subinterval is from 3 to 6, and I look for the lower Y value. And rather than write 4, I say, hey, where does 4 come from? It's F at 6. And the next subinterval from 6 to 9, I say, what's the lower? It's 3, and 3 comes from F at. Then I go to the next subinterval, 9 to 12. What's the lowest Y value? It's F at 9. Then I change up and I go to 12 to 15. What's the lowest value? 0, which is F at 15. And the last is F at 15 again. You see where I'm coming from? All right, now then we have to go back and do that again and look at the tables, but this time we're actually going to use the values. So F at 0 is 5, F at 6 is 4, F at 9 is 3, there's another 3, and F at 15 is 0. All right, so my estimate then is, what we got there, 10 at the back end plus 5, so 15 times 6, 45. I agree. All right, you with me? Now I can be sure that the true area is less than or more than that. That's an underestimate on being conservative. All right. Estimate the area under 0 to 18 using 3 circumscribed upper rectangles of each equal subdivision. So in this case, as the name kind of indicates, use the greatest y value in the whole interval, whole subinterval. Now that doesn't even need to mean at the outsides. It might be on the inside. So let's go here. What's the delta x? 6. 18 divided by 3 is 6. The area is approximated by delta x times how many heights? 3. All right, we said delta x is 3. All right, so in the first region goes from 0 to 6. All right, so I'm going to focus on 0 to 6, and I'm going to look in that whole region. What's the lowest y value? F at 6. And so I'm going to say I'm going to choose F at 6. We're supposed to use the upper y value, yeah? My bad. I was thinking lower value. So in that whole subinterval, I'm looking for the greatest value, which is F at 3. Sorry, I was still in lower mode. Our delta x is, obviously I'm having a little carryover issue for 3. F at, so we're cool at 6, and now it's F at 3. Sorry about that. Are you good? Okay. The next subinterval is from 6 to 12. And I look for the greatest possible value, and in that case, it's F at 12. And the last subinterval is from 18. I'm going to use F at 12 again. All right. With that, then, my estimate is 138. I'll take your word for it. I can't see it. Yes?
So could you do this based on just a graph, or are we always going to give a table? Like if they were to give us a graph and say...
Oh, good call. That is not unheard of. The table's far more common, but you should be able to work from a graph also. They will sometimes give you a graph. That's a good question.
Give us an example. How is that? How would you... Yeah, how would you...
You would have to, they would have to have the points clearly labeled. So if I said, here's 4 and that's 2 and that's obviously 2. I would call a problem something like this. Actually, let's go here. I'll go this way. Get some sign action in there. What do you say? Okay. If I said, hey, what's the area under the curve? Estimate the area using 2 midpoint rectangles. This is a little past what we're going to do. We haven't done sign stuff yet, but what's the delta x? Delta x is 4, okay. And I'm just going to go straight to this. The first height then would be F at 2, and the next height is F at 6. F at 2 is 2, and F at 6 is -3/2.
What?
The 6 is here, and it's halfway between. Okay, so -3/2. So yeah, that's possible, and that absolutely kooks people out to see a negative height. It is what it is. It does happen, and we will deal with it. But yeah, it's possible. Okay. All right. Homework questions from last night.
Hold on, I just want to see which problem.
All right. I have a lot of the replacements pasted in. If you want to go over those, you can, but whatever you want. 2? 21. Somebody say 9?
Yeah.
9. All right. Okay. Need another second to get situated or go? Okay. So two, first of all, let's step back and talk about the big idea that you'll eventually get to on two. It's easy to get lost in the what's the point of it all kind of thing. Imagine I made a box that was meant to hold 64 cubic inches. I could make a really wide, really short box, and it could hold 64 cubic inches. I could make more of a square kind of cube box, and it might hold 64 inches. I could make a really tall box. It could hold 64 cubic inches. All those could hold 64 cubic inches, and yet they'd all have different amounts of surface area required to make the box, yeah?
Yeah.
Because they are a different surface area, the cost of this might be a heck of a lot more cardboard and cost to make than this one. So the idea of calculus, at least business calculus anyway, is called optimization. What's the best way to configure the box so that, yeah, it holds 64 cubic inches, but it uses as little cardboard as possible? That's what this question is getting at. We're just not doing the calculus part of it yet. All right, so they're saying it's got to have a square base, and the height, I don't know what's going on there, but it's got some kind of height. Even that has infinitely many configurations. They say the volume is 64. I'm given that the volume is 64. Express that. What do we want the surface area in terms of x only? All right. So let's start with the question. If I'm not sure, rather than start with the givens, I'm going to start with the question. What's the surface area of the box? 280. Beautiful. Okay. So in this case, in terms of what we're given, isn't area of the base x squared and perimeter of the base 4x's? All right. At that point, then, I run into my problem. I say, okay, they say it's supposed to be in terms of x only, and therefore this is what draws my attention. This is bad. It says x only, and it's not in terms of x only. It's got an h. So I need to put something in for h. That's where I say, what can I sub in for h? That's where the volume comes in. They didn't give it to you for no reason. The volume of 64 is equal to x squared h. Should I solve that for x squared or solve it for h?
H.
Yeah, h is 64 over x squared. So if that goes in there, then s is 2x squared plus 4x times 64 over x squared. And for this problem, that's it. That's all you're supposed to do. Now, I can tell you the why you do that is because it's a heck of a lot easier to take a derivative now, or find what s prime has. S has a maximum or minimum. Do I want to minimize surface area or maximize? Do I want as much cardboard as possible or as little? Yeah, in this case, you'd actually want to minimize the cardboard. You want to find where s prime goes negative to positive, and we'll do that later. That's the optimization part. But right now, you're done. You with me?
Yep.
Okay. 5, make sure you use the product rule here, not a chain rule. Some people think that's cosine of. It's not. It's cosine of x times. It's product rule, not chain. 21, is that a replacement or book? All right, that's a hard one.
Good morning, Dublin Jaguars. Please rise for the Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All right, first look at the domain. The domain is x has to be greater than or equal to -1. Now the calculus.
Water in the gym locker room, you need to keep it clean and picked up at night. Anything on the floor or on the benches will be thrown away at the end of the night.
The product rule
Bags should be
says
closed and placed under the
first stays
benches.
the
The locker
same,
should be used, and the area should be clean and
and
organized
the
all
derivative
day
of
and
the
night.
second
Thank you for your cooperation.
is 1/2 x plus
Make your
1
voice
to the
heard.
-1/2.
Diversity GSA Club will host a Make Your Voice Heard open
Yes, you
mic
could
on
say
the
times
public
derivative
sector
inside, but that's
solutions
just one,
of the
yeah.
WPQ community.
Plus second
It
stays
comes
the
through
same,
tomorrow, September 27th,
and the derivative of the first is -3.
on Friday and join us in
Do you agree with my derivative?
See you there.
Okay, now here's the hard part by far is the
Tomorrow there are
algebra.
assigned groups. Check the mentoring bulletin board out at the cafeteria if you
So
forgot
if I
where to
clean
go.
this up,
See you there. All students, do you like food trucks, music, yard games, and Then come to the homecoming bonfire next
It looks
Wednesday,
like that.
October 2nd. Bring your families and enjoy the festivities starting at 5 p.m. We will light the bonfire between 7 and 7 p.m.
Yeah, I'll get a
Today
common
is a busy day
denominator.
with college visits and the counseling starting at 10:30 a.m. with John Brown University, followed by the University of Denver, Azusa Pacific University, and Westmont College. Stop by and get a pass as these visits are during class time.
This side will not change. It had the common denominator.
Missouri University and Sierra Nevada College.
This will be there, but what will I multiply it by?
Secondary education, there is no better place to explore your options than at
Right?
NAC National College Fair on Sunday, September 29th from 1 to 4 p.m. at the Denver Market. Admission representatives from
Negative
schools
3
across
times
the country
2
are
is
gathered in
negative
one
6.
place. Learn more
What about the root
education
times
and
root?
sort through the qualities you're looking for in college. Dad, your varsity cheer team is selling 3,000
That's
scrunchies for $4.
negative 9x plus
They
6
come in 2,000 Dagford and 1 green and
over
white
2 root x plus
They're
1.
selling them during both lunches or
We
message
agree.
one of your DHS cheer team
Minus-
members or the
minus
DHS
6,
cheer
right?
team on
Should be minus 6?
They're selling very fast, so get yours now. We're good to go today. Homecoming ticket sales start today at both lunches for $15 each.
Okay,
Lost and found is on display in the
0
front
undefined.
office.
You with me?
If you're missing items.
Yep.
Almost there.
Donated this
The
time.
derivative is 0 if x is,
Seniors, be sure to get this counseling this
is that top 0 or bottom 0?
your name for your diploma.
Top 0. What makes the top 0? Negative 2/3. Is that in the domain?
Like to take the AP language and English exam on May 13th.
Yeah,
Please come down to counseling to receive the
Is
registration
negative
form.
2/3 greater
You
than
know,
negative
over
1?
the course of that lesson, if we
It
have
is.
students to sign up, we can offer
Okay.
the exam. The form needs to be turned in by
Derivative is
September 30th,
undefined
plus
if
$95 to Mrs. Schreiber. Hey Dad, do you want
x
to help
equals
save life?
denominator equals 0, so x equals negative 1. Is that in the domain?
Next Tuesday.
It is.
Donators must be at least 16 years old.
Those are two
Students
critical
aged 16 and 17 need to fill out the parental permission form.
Okay.
Be sure to eat before donating blood. Sign-up sheet and
Right.
parental permission form will be located in the admissions office. Seventh graders last year's RSV will not be required to complete for survey today because it is not working. We'll reschedule it for another day and let you know. Be sure to sign up for 7th hour. It's time for your daily day of the day.
This was factoring by grouping.
Make sure to eat some pancakes and have a great day.
That required skill in cube factoring. Feels like this is 0 if x is 2, 1, or negative 1, yeah? Okay, so, and I'm just going to cheat and say the derivative goes negative, positive, negative, positive. So I feel like you should have 2 mins and a max in your conclusions. Cool? F has a max at. You get the idea. Have a great day. Right at the bell. Hi. Oh, skip that one. That's not something you've done before.
John tomorrow, should I get the one sheet today or?
I don't have it made. I will. It'll be posted on my website. It probably won't be posted till first period tomorrow. Okay, sorry. Have a good day though. We're good. You're welcome. Have a good weekend. Or weekend, sorry. Day. Wishful.